New Open Access Journal. Good afternoon, I'm Caroline Champney. I'm the publisher of the New Open Access Journal ePrime here at Elsevier. And today I and Karanesh, who's one of our early career editorial board members, we're excited to welcome you to the next webinar in the series. So Elsevier's ePrime is a new open access fast turnaround journal in electrical engineering, electronics and energy. It was launched in 2021 to help increase the impact of your research across disciplines. And today our webinar speaker is Professor Christoph Markaides. He will present on the next generation of hybrid PVX technologies for high performance solar utilization. So we ask you to ask your questions throughout using the Q&A, and at the end we'll pick those up. Karanesh will guide the question. Before starting the presentation, I'd just like to introduce you to Professor Markaides. Professor Christoph Markaides is a professor of clean engineering technologies and head of the Clean Energy Processes Laboratory at Imperial College London. He's also editor-in-chief of the Elsevier journal, Applied Thermal Engineering. He specializes in applied thermodynamics, fluid flow, heat and mass transfer processes as applied to high-performance devices, technologies, and systems for thermal energy recovery, use, conversion, and storage. He's published 300 journal papers and more than 350 conference papers. And Professor Markaides also has won multiple awards, including the IChemE's Global Award for Best Research Project, that was in 2018, the IMechE's Donald Julius Green Outstanding Paper Award in 2016, the Engineers Without Borders Chile Challenge, that was in 2020, as well as the Imperial College London President Award for Teaching and Research Excellence. Professor Markaides' papers are regularly selected for covers or as the most cited and downloaded papers in journals, including a featured paper in Light and Science and Applications, that was in 2021, and also a front cover paper in Nanomaterials Science, also in 2021. So without further ado, I'd just like to pass you over to Professor Markaides to take you through his presentation. Welcome. Thank you.
Thank you very much, Caroline, for the very warm welcome, very kind introduction, and welcome everyone to my talk. As you can see from the title, we're going to be covering solar utilization technologies. And you'll see a term which is non-standard. I think everyone will be familiar with PV. I'll introduce this in a minute, but everyone will be familiar with photovoltaics. Some people might be familiar with something called hybrid PVT, where the X is replaced by a T, which stands for thermal most of the time. But this term PVX is something that we've coined together, so it's not a standard term that you would find in the literature. And I'm kind of hoping that I will explain during the course of today's talk why I believe this is quite exciting and interesting, and the diverse range of solutions that we can have under this kind of umbrella term of PVX. Okay, so I just have a couple of very quick slides that I'm not going to spend any time on. I just wanted to say that, yes, this is us. We're based in the Department of Chemical Engineering at Imperial College London. We're split into divisions. We're a reasonably large group with a lot of activities. Today's talk falls under, this kind of general research direction in the group, which is to do with high performance solar systems, technologies, right? Energy technology. We do all sorts of other things. We recently also published a paper in ePrime, which is about hybrid nuclear systems, but it's not directly related to what I'm talking about today. There's a slightly different theme of research within the group. I don't have time to introduce everyone, but I did want to have at least one slide where I have a photo there and some name. You can have a look there at the people who over the years. So I've been at Imperial now over 15 years. This is work. Yeah, what I'm covering today is basically around about 15 years of research. You can see here the people over the years that have all done their PhDs or have worked as postdocs in different areas that I'm covering today. I just wanted to say a quick thank you to everyone who's interacted with me on this subject and who's contributed to the talk today. And before I start, this is the last introductory slide. I wanted to kind of make sure that we focus a little bit because, solar energy, as you can see here, or technologies, solar technologies, there's a very, very wide range of types of systems that you will find out there. You can see on the top right-hand side of this slide over here, massive power stations with towers and many, many mirrors focusing light, basically generating power at megawatts, 10 megawatts, 100 megawatt scale. So, these are what people might refer to as centralized power generation systems. But, you can go all the way from that to, very small type systems that you can have in your home. For example, a couple of PV panels on the roof or a solar hot water system on the roof. So there's a very wide range of technological options available to us. And typically, we can try to categorize what's going on in terms of power output. So let's say how big the system is, right? On this axis here, we have power output from the system. But also what's very important when you're dealing with thermal energy is also to speak about the temperature, right? At which a system might be operating. And so you can have things that are lower temperatures and things which are very high temperatures. If you're concentrating sunlight, you can reach very high temperatures. And although we work and have interests, across the board here, obviously there's an interest in all sorts of technologies at different scales of application, at different temperatures, different concentration ratios. My talk today is primarily kind of focusing on this red box over here, right? So we're talking about what's called distributed applications, which means that the technology gets a little bit closer to the end user. This is not a power station in the middle of the desert, right? With lots of mirrors and massive towers and big turbines. These are small systems that, hopefully people can buy and put on their roofs. So this is what distributed means: small scale, closer to the end user. And because of the fact that they're distributed and you don't really have control over where you will put them, in the same way that you would have control if you said, okay, I'm building a power station, where is the best place in the world to situate these kinds of power stations? And typically you'll end up in Chile or South Africa or Australia. But here, you might be someone living in the UK like me in London right now. Okay, there's a little bit of sun. So I don't have control over where I would place my solar system. It would be on top of my roof. And because of that, we tend not to want to rely on something called DNI, which is direct irradiance. Because clouds are passing, there are buildings close by that can cause shading and so on. In that case, we don't really want to rely on high levels of concentration. So we don't want to be operating out here where the optics are very important. We want to operating this kind of low temperature range, which does not rely very much on basically uninterrupted sun coming onto your system. So that's what we're focusing on today. And there are already available options, which I've mentioned quickly. So let's go quickly through this slide. You know about photovoltaics. They are an excellent, mature technology with lots of exciting research as well, whose main job, I should say sole job, is to generate electricity from the sun. And they do this very efficiently and very well. And then on the left-hand side, you'll also see these, they're called solar hot water systems or solar thermal systems. And remember, we're talking now as systems that you can install on the top of your roof, right? I'm not talking to you about utility scale or, large power station type systems. These are, the kind of things that you would put on your roof and hopefully you'd get some hot water, and that way you displace the need for gas burning. So these are, very, very mature technologies, massive global markets. We know them very well. We've had them for decades and decades. But of course, one thing to realize is that, a household, right, an end user doesn't have the need for electricity or the need for hot water or heating. What they really have is an electricity for both they have a need both for electricity and for hot water and heating for their home. And the question therefore arises is, okay, so other than me buying two separate systems, right? So I can install PV panels, I can then install a solar hot water system on top of my roof. Is there something a little bit smarter that we could be doing where, we have a solar system and that solar system can be outputting both of these vectors and delivering both of them simultaneously to the end user? And of course, the answer to that question is, well, yes. And we've got this thing on the right-hand side called the hybrid PVT, where, as I said before, T stands for thermal. collector technology. And this type of technology, you can see here, it kind of looks like a PV. So it's got cells on top. The sunlight hits these panels, they generate electricity. So, okay, that's relatively straightforward, sort of similar to PV. But what you can also see is a sort of a pipe here extending from the roof into this PVT collector. And what the pipe is there to do is to circulate a flow of water to this collector, which then gets heated and then gets delivered to an end user. So basically what we're doing here is from the same solar panel, we're generating both electricity and heat. And it's known because there have been many, many studies being done. We've also looked at this. Many, many people have looked at this. It's a very popular research question. So we know that these collectors, which sort of simultaneously generate heat and electricity, are more efficient than side-by-side systems. So than by purchasing PV for the electricity and these solar hot water systems for the heat. So we know they're more efficient, which means that they're more space efficient as well. So these are nice systems if you want to think about deep decarbonization, if you want to decarbonize both electricity and heat. Now, the original motivation, other than just saying, well, can we do both jobs with one collector, is captured very, very nicely on plots like this. So what you see here on the left-hand side axis, so this vertical axis, is the efficiency of a PV panel or a PV cell relative to its efficiency at 25 degrees as a function of the temperature at which this cell operates. And what you can clearly see here is that irrespective of which photovoltaic technology or material you want to pick, and you see many of them on this slide, so I'm not going to read it out. There are many different types of materials that you can use as a photovoltaic, to use in photovoltaic panels. But irrespective of which one you pick, you have something called the temperature coefficient, which is basically a reduction in the efficiency of conversion from sunlight to electricity depending on the temperature. And this is actually a bit of a problem, and it's a very significant problem. So if you really think about it, where would PV panels be most efficient or most useful? Where it would be exactly in those places of the world where, right, you have a lot of sunlight. Now, typically the places where you have a lot of sunlight, and I should say also, if you happen to be in a place where maybe you don't necessarily have a lot of sunlight, but at what point of the day or at what point of the year would your panel be generating the most amount of electricity? And the answer is, well, in the middle of the summer when you have a lot of sun, right? Now, in the case where you have a lot of sun, typically what you also have, right, is high temperatures. So both your ambient temperature goes up because it's nice and warm, and the temperature of the panel itself gets very hot because it's being heated by the sun, and there's a very high level of irradiance hitting the panel. So it heats up, and in some hot countries or in the middle of the summer, the temperature can basically be off the chart, so to speak, in this diagram. It could be to the right of this 70 degrees, could even reach 70, 75 degrees sometimes. And you can see that the loss in efficiency relative to what you would get at 25 degrees is very significant, right? So we're talking about 20, 25% efficiency loss in the worst case. And this is a very significant loss. And this problem description, if you want, which is that if your cells get hot, if your panel gets hot, its temperature rises, you lose electricity, also kind of suggests a possible solution, which is, well, okay, if we're very hot and we're somewhere out here for a crystalline silicon type panel, is there a way to cool our panel and to basically recover some of that electricity that we've lost, right? And so this kind of motivates this idea that, can we pass some cooling fluid through the collector, cool the cells down, get more electricity, but of course, at the same time, since we're heating, the heat is going from the cells into our whatever coolant fluid we're using, now we have a thermal output that we can deliver to someone, right? So we're doing two jobs, two birds with one stone. We're cooling the cells, getting more electricity, plus we now have this heat that we can deliver to the end user. So we have this hybrid system. And there are many available products on the market already. We didn't invent this, of course. Many people have proposed, and many companies, different types of products. You can see on the left what's called unglazed designs, where the PV cells are on top. They're stuck to this kind of copper plate, and there's this coolant, typically water, it could be air, could be water, could be any other fluid, to be honest, passes through the system. And the idea here is that, can we get some of the heat inside these cells? Can we pull it out into this fluid stream and then deliver that fluid stream to an end user, right? That would be a useful thermal output. You can cover it, so this would be starting to look a little bit more like a thermal collector. You can have glazed designs, which is basically just this glass cover that you can see on top. There are many, many different designs, but in all of these cases, I think what's very important, I'll highlight it here and I'll come back to it on the next slide, is that what your incentive in these types of designs, which I call conventional designs of PVT collector, your incentive is to make the thermal resistance between the cells and the fluid which is being used to cool the cells as small as possible, right? So if you make this resistance small, you can pull the maximum amount of heat away from the cells, so you can have maximum cooling, let's say, right? Now, one consequence of having a very small thermal resistance between two things isn't just that you can remove a lot of heat, that's good, but it's also that the temperature of the cells and the temperature of your coolant fluid are locked together very tightly, they're coupled, right? So if you have coolant fluid that is at 40 degrees, your cells would be at 41, 42. They would be a very, very, very close temperature to whatever your thermal output is. And this can be a problem, and I'll discuss this in a minute. But before I do, this is some work that Maria Gerando, which at the time was a master's student, did. And you can see there, I have some references on the bottom right-hand side for people who are interested. But where she went to a number of manufacturers of PVT products, and she found different PVT designs, and she plotted there. So here we have a thermal output, but you can imagine dividing this by 1,000, which is the standard irradiance level, right? Which is where all of these products are tested. So this would be a thermal efficiency. Let's think of this as a thermal efficiency on the left-hand side here, and an electrical efficiency on this bottom axis. And what you see here is that those two things are correlated, right? So as the manufacturer tries to design something which is maybe a little bit better electrically, so we say, okay, can we design a panel that can give us a bit more electricity? We lose some heat. And if we say, well, okay, let's design a panel which is very good in terms of how much heat it can deliver, somehow you pay a penalty in terms of how much electricity. So we basically refer to it as a trade-off, right? You can't have a lot of heat without sacrificing electricity. You can't have a lot of electricity without sacrificing the heat. And again, this throws up a question, which is there a way to break this trade-off, right? Is there a way for us to design panels where, getting a little bit more electricity doesn't mean that we have to sacrifice the heat and vice versa? So we'll keep that in mind for now, right? This is one challenge. The second challenge when we're talking about heat, as I said at the beginning of my talk, is that it's not just about how much heat we're generating. So remember here, I just said, oh, this is how much heat we're getting. But it's not enough to just talk about how much heat. It's also very important to talk about at what temperature, because as you can see here, and I'm not going to start throwing very complicated terms like exergy and availability out, but I'll just say that the higher the temperature that you're able to deliver a thermal output to someone, the more useful things you can do with it. And you can imagine that if I give someone 30, 40 degrees hot water, maybe they can boil pasta, but there's not much more they can do, right? But the higher the temperature that I make the same amount of heat available, the more useful things we can do with it. And you remember what I said before, that in conventional designs, so I'm going back here, in conventional PVT designs, the temperature of the cells and the temperature of the thermal outputs of the heat that you're delivering are very closely coupled. They're very, very close to each other. So if you want to deliver high temperature heat, which we've just said would be beneficial thermally, this also means that your cells need to be running hot. And as you've just, I think, heard me say, running your cells hot is not a good idea. So this is another trade-off. If we want a good thermal output, we need to sacrifice our electricity because the cells will be running hot. So again, the question arises, can we break the temperature, right, link between the thermal part and the cells? And the answer is yes. There is a way to achieve this kind of decoupling between the thermal side and the electrical side in a way where we're not sacrificing one in order to gain on the other side. And it's called spectra splitting. So this is a sort of a design methodology, a design approach, which is different from the conventional approach I was talking about before. And what do we do here? Well, we realize that photovoltaic materials are not sensitive to the entire spectrum, so to all the colors of light coming from the sun. So on this plot here, what you can see is energy distribution. So this black line is what's coming from the sun. And these different colors you can see here are basically the sensitivity, if you want, of the cells to the different colors of light. Now, this bit here is visible, so that's the part of sunlight we can see, but there's a part we can't see called infrared, and there's also a little bit of UV out here. You might have heard of UV. And what you find is that different photovoltaic materials, of course, have different sensitivity ranges, but that's beside the point. If you pick any one of those, you realize that, well, they kind of sensitive to some part of the sunlight, right? But not to another part. And so then, from that, we can start thinking about designs where we can take this part of sunlight that the cells are not sensitive to. Remember, this part out here, these wavelengths, if you want, this energy, can never be converted to electricity. So why would you want to send that to the PV, right? Why would you want to send that to the cells? All it's going to do is it's going to end up heating the cells unnecessarily. So you can take that part, send it to a thermal absorber, heat up that absorber, and keep that thermal absorber now separate from the PV cells. The idea here is if we split physically where the PV cells are from, let's say, the hot part of the collector, this thermal absorber, this could be hopefully operating at a high temperature, and this could be operating at a lower temperature, right? And now we've broken this link between the two. So hopefully, because this is cold, it's more efficient electrically, and now this can be hot, and it can be giving us a high temperature thermal output, and that's beneficial for us. So there are many ways to achieve what I just said. You can do it by, taking sunlight and splitting, right, the different wavelengths, some of which so this is by preferential reflection. So here some wavelengths are going to be transmitted through some filters, some of it are going to be reflected, and you can see here the thermal absorber, right, is separated from the PV module. It's not in contact anymore like it is in conventional design. So the PV module is here, receives some part of the light, the rest of it goes to the thermal absorber, or it can be done by preferential absorption. So here the sunlight comes in, some of it gets absorbed to heat something up, and the rest of it flows through to the PV cells where you generate electricity. You can see here anyway, without me going into the details, there are different ways in practice to achieve this splitting where some bit of the light goes to heat something up and some bit of the light goes to the cells for electricity generation. Okay. And this is how you would achieve what I said before. So we break, right, this link between the temperature of the cells and the temperature of the fluid. So hopefully our fluid is hot and our cells are cold. And there are many designs, I'm just giving a couple of links here. If you want to go into the literature, many people have looked at this. So as I said before, different designs based on preferential reflection or absorption. Here you can see preferential reflection or selective reflection solutions, whereas, part of the light is reflected somewhere where the PV cells are absent. Okay, so all of that was a bit of an introduction in terms of, okay, what sort of has come before us and what sets up what we want to do. And what I'm going to do now is start with presenting, a very high level, easy kind of roadmap, if you want, what the steps in research that we've been following over the last, 15 years, looking at different issues of how to kind of improve this type of spectral splitting PVT collectors. And I'm going to go from, let's say, fundamentals, a little bit more like science, materials, processes, then go one step up to the level of the component, the collector. So let's say technology level work that we've done. And from there, one level up to the system, right? So the system would be, let's say, trying to understand once you have your nice, fancy panel and whatever it is, that's great, but that panel will interact, right? And operate within a wider system. And you need to know what this interaction is going to do in order to understand the real benefit, right? In terms of costs or whatever it can deliver to an end user, right? So we have these three levels of abstraction. And I'll tell you a few interesting things we've kind of been doing over the years in each one. So let's start from the first one. So I want to talk about two issues which are very important when it comes to, let's say, the more fundamental work. One is heat loss suppression, and the second one is spectral splitting. So spectral splitting, I think, is kind of obvious because we've said, oh, the spectral splitting is wonderful and it can give you all these benefits. But then the question is, well, yeah, okay, fine, that's great. And you've shown us some ways to do it, but what material would you pick to do this magical filtering that you're talking about, right? How can you actually achieve it with in practice? And so we'll talk a little bit about that. But the first point here about heat loss suppression is also quite interesting, in my opinion, because Unlike photovoltaics, where any heat that your system gains, right, is parasitic, as in it will lead to a loss. So your incentive in any PV panel, right, is just lose as much heat as you want, as you can, because the temperature of that panel will come down and you will gain your electricity. So what we're basically saying for PV panels is the PV panel is only there to deliver electricity. Any heat, right, that's generated internally or gained should be lost immediately, right? However, we're talking about PVT, right? So there's a thermal element to what we're doing, and heat is delivered to an end user. So us losing any heat to the environment or anywhere else is a problem for us, because heat is a useful vector of energy we want to deliver to our end user. So we can't afford to say things like, oh, well, let's just reject some heat to cool down our cells. We want to capture that heat. And capturing the heat is the same thing as saying, okay, let's not lose it. And that's what heat loss suppression means. How can we suppress the losses of heat from our collector? Because heat is very important for what we're trying to do. Now, in the types of collectors that we're looking at, there are two main mechanisms, right, of heat loss. One is through convection, one is through radiation. And I think I won't say much, because I'm kind of, I hope the audience is aware of kind of basic heat transfer, but very quickly, convection is basically just, you know, thermal energy lost from our system due to the fact that we have air flowing over the system, and this air basically picks up some heat. You know, the air gets hotter and then gets transferred away, right? So it's basically a mechanism for us to remove heat from the panel. The second way for us to lose heat from our panel or from our collector is through radiation, right? So every surface that exists at some temperature above zero will radiate energy out. Just like the sun is at some temperature and radiates heat to us, we also radiate heat outwards. And these two mechanisms, so this convection and this radiation, as I said before, in a PV panel, you want them to be as high as possible. You don't want to lose, to trap this type of heat, of course, because you just end up heating your cells. But for us, these are parasitic. They are losses of energy that we ideally want to trap, right, and send into these coolant pipes and then deliver to an end user. So how do we do this kind of suppression? How do we cut down the convection and radiation in our systems? Convection is kind of easy. That's what you do in solar thermal systems anyway, right? So I think in the beginning of my talk, you'll have seen that solar hot water system with those glass tubes that you might have seen. Well, those glass tubes are there basically because they seal something inside, which is a thermal absorber, and then you pull all the air out. So basically it's a vacuum, right? And vacuum is very good for suppressing convection, because basically there's no air there, there's no gas to help transfer the heat out from the collector. So that's a good way to cut down convection losses. It doesn't have to be a vacuum, right? So you, as I said, you know, you can have this, you can introduce a glass layer here, and there's a bit of a gap, and now you can pull the air out of this, and that would be a very, very good way to suppress convection losses. But there are other ways to do it. There are people that, you know, add heavy gases, or there are other ways to suppress convection losses, but that's not the really kind of exciting part, because let's say that's what you would do anyway for a solar thermal type system without the PV cells. Let's go to radiation, because I think that's a little bit more interesting. One thing to do with radiation is to, as I said before, you try to, of course, you want to trap as much of the sun coming in, and you want to not radiate the radiation back out. And the way that you can do this is by coating the surface of your collector, which is facing out towards the sky, with some kind of coating, right, that reduces the emissivity of that surface. So if you reduce the emissivity, that means that you're not emitting as much radiation outwards. Now, what's the problem with this? Well, the problem with this is that there's a principle in physics that says that if you want to have a very low emissivity, as in if you don't want to emit radiation, you are also not very good at absorbing radiation. And I think everyone will be comfortable if I say, well, a solar technology that can't absorb any sunlight is probably not a very good solar technology, right? So what are we saying here? What we're really saying is that we somehow want to find a way to absorb the sun's energy, so that the absorption needs to be high, but we don't want to emit radiation out to the sun, or to the sky, I should say. And so how do we do that, right? How do we do that? Well, one thing we do, and I want you to focus on the right-hand side first here. One thing we do is that we kind of spot this very interesting characteristic. So this is just to kind of present this slide here. We've got wavelengths here. So this blue is the energy coming in from the sun. And you can see that, okay, it's not monochromatic. In other words, there's UV out here, there's infrared, there's the visible here, the part that you can see. But what's very important here is that, okay, there's a distribution of wavelengths or energies, however you want to think about it, coming in from the sun. And this red bit here is, let's say, the radiation which is being emitted outwards. And what you can see is that these two parts, right, are separated. They're separated, right? So there are different wavelengths. And so this is very good for us because it basically suggests that if you can find some kind of magical material that absorbs the sun, so it absorbs at some wavelengths, but does not re-emit at other wavelengths, then we basically solve this problem, right? And there are materials that can do this. This is work done by a very good colleague of mine, Ned Eakins-Dawkes, is based now at the University of New South Wales in Australia, to look at so-called selective surfaces for emissivity control in order to achieve exactly what we've said, right? So you want your cells to be having a high absorption here and a low emission out here. And you can see here, this black line is just a conventional silicon solar cell that they bought, which they coated with something called ITO. And you can see here how you can reduce the emission at these long wavelengths, right? Where normally you'd be re-emitting a lot of energy outwards, but if you can bring this part of the curve down out here, you can suppress those radiative losses. So this is possible to do. The second thing I want to mention, I think at the beginning was, you remember we said, how can we absorb or reflect, or, right? We can do this kind of spectral splitting. Well, of course, that's easy to say. The more difficult question is, well, that's fine, but which part, again, this is the distribution of energies coming from the sun, infrared, UV, visible. Well, how do you know which part of the sunlight, you would give to the cells, and which part of the sunlight you would send to the thermal absorber for heating? And without wanting to go or going into a lot of detail, again, in the interest of time, there is a nice work that someone called Gan Huang did with me a few years back, where we can define some kind of performance metric. Let's call it a total efficiency. Now, this is a sort of a weighted total electrical output and thermal output. And once you define, let's say, the relative value of electricity and heat, so once you say how important the electricity versus the heat, or I should say the electrical versus the thermal output, right, from the system is, then there are maps that he developed, which can give you the ideal optical filter that would give you the basically maximum total efficiency in each particular application, for different types of cells, for different types of concentrations, for different types of all sorts of things. And I would say very quickly, I said value, right? Because the relative value between electricity and heat can be defined in different ways. Some people might talk about thermodynamic value. How do I convert heat to electricity so I can make these two things comparable, because they're not really? Or it might be an economic value. What is the value of 1 unit of electricity that I generate in terms of cost, for example, relative to one value of thermal energy output, depending on the temperature, of course. So there are different ways to define what this relative value between the two things is, but whichever way you decide is the best way to do it, once you've defined it, there are maps that tell us exactly where you need to cut the spectrum, which part needs to be sent to the PV and which part needs to be sent to the thermal absorber. So we can find from maps here what the ideal splitting is, but how do we achieve it in practice? Well, you can do it by using nanofluids. Many people work in this space. We've done very little work here, but a little bit. Nanofluids are very challenging because there are stability issues. I think a lot of people might be aware of nanofluids and their kind of role in enhancing heat transfer. Here, we're not talking about enhancing heat transfer, right? We're talking about absorbing preferentially part of the sunlight so that the rest of it, let's say, gets transmitted to your cell, while the part that gets absorbed goes into the fluid directly to heat this fluid up. And there's, hundreds and hundreds of papers in the literature about, okay, which material, what size of particle do I use, what concentration of particles, which shapes, different types of things that you can do to these particles to absorb different bits of sunlight to create, or try to have a filter that you're aiming at, okay? So this is one way to do it, with the challenges that I mentioned before: stability, lifetime issues, which we're not working on, but there are many groups in the world aware, of course, of these challenges to do with the use of nanofluids. Haven't resolved it yet, but there are people working on this. So this is one interesting, let's say, avenue of trying to achieve this kind of ideal filter, let's say with some kind of mixture of nanofluids that can absorb in the right part of the spectrum that we already know and we're already targeting, because we have our maps that tell us what the ideal shape of that absorption should look like. We haven't done a lot of nanofluids, but what we're kind of looking at more and have an interest in is actually using liquids to absorb, because liquids have molecules and molecules have bonds and atoms. And so these molecules have, of course, all molecules will absorb some part of the light, so they will interact with the light, and the length of the bond and all sorts of things will determine which part of the wavelength they can interact with, so they can absorb some part of the sunlight. And so what you see here is, on the left-hand side is, from a database, different types of bonds, different types of molecules, bits of the spectrum that they can absorb, right? And so what we've been trying to do is develop a tool that kind of reverse engineers this, right? So if we know we need a particular part of a spectrum to be absorbed, what combination, right, of groups of molecules or atoms or bonds would you need, right, to create this kind of absorption profile? And so this is called molecular design, right? So you don't necessarily start by saying, oh, what would happen if I have this? What would happen if I have this? You say, no, this is what I need. I need a spectrum with a particular absorption profile. How do I achieve it? So what's the optimum combination, right, of molecules or bonds to achieve it? Okay, let's go to the level of components, so the collector. How do we then go from, oh, we have a nice material that we can use to suppress, so we can have a nice coating that suppresses radiative losses. We picked a nice spectral splitting material to absorb here, or reflect there, or transmit there, or whatever it is we've done at the materials level. How do we go then from there to building a collector that we can take outside and harness all these kind of wonderful properties and characteristics at the materials level? Well, it's the usual story when it comes to engineering, right? So we have modeling approaches, right? So we typically have a lot of work on something called COMSOL. These are multi-physics problems. We have fluid flows, heat transfer. We have the electrical side as well, because we have cells generating electricity. And of course, the electrical performance of those cells is a function of their temperature. So we have all these interacting physical processes taking place. And typically what happens in these types of modeling approaches is, we would have some three-dimensional model of, or whatever our collector looks like, right? So here you can see an evacuated tube type PVT collector. I'll discuss this on a bit on the left-hand side in a minute, but you can have this evacuated tube type collector. We have your PV cells inside. It's evacuated. Remember, you're evacuating this to suppress convection losses, and then you have your flow of fluid. And the questions, of course, are, yeah, that's great. You can do all of these things, but yeah, what sort of temperatures do you reach? What different radiance levels? What type of efficiency would you expect to get? And so on. So, you can do this with these kind of dynamic models, three-dimensional models. I'm showing here on the left-hand side an example of, a real example of a company who's developing a sort of evacuated tube PVT collector. They're called Naked Energy. They're a UK-based company. And what you see here is very, very interesting technology. What you see here is basically two tubes, one next to each other. We had a project with them a few years back. to look exactly at this, what sort of performance benefit you can get from these types of collectors, what sort of performance you can get. Now, there's the evacuation part. So the cells are inside the glass, and there's a bit of a vacuum between the two to suppress convection losses. But there's another very interesting characteristic here. If you look at this photo carefully, you realize that the tube on the left has cells that look blue, right? So that's what normally PV panels look like. But the one on the right-hand side, you can see the cells are a different color, right? They're sort of greenish yellow. And that's because these cells have been coated with this ITO coating that I mentioned before to suppress radiative losses. So ideally, what you're wanting to see here is this panel on the right-hand side thermally outperforming the panel on the left-hand side, and I'll show you some results in a minute. But at the level of modeling, yes, you can have your tools and you can start playing with that. There's also testing that needs to be done. So, the modeling can only go so far. At some point, you have to do tests, and typically those tests can be indoor tests. So we have something called solar simulators, and you can put whatever collector technology you have under a solar simulator and measure thermal and electrical performance, as you see here, thermal efficiency, electrical efficiency at different temperatures. And then, of course, there's also outdoor testing where you go outside. But before I go to that, I just wanted to show you here very quickly. This is not a spectral splitting collector, right? This is just a collector from Naked Energy. And these are tests that we did as part of this project that I mentioned a few years back, funded by the UK government, the EPSRC, where we were able to prove with a very, very, very minor reduction in electrical performance, you can get a very significant benefit in terms of your thermal efficiency, right? Which you can see here on this plot with the coated collector, right? With these coated cells can achieve a much higher thermal efficiency than the one which is uncoated. The reason for that, of course, is that you're not losing all that heat radiatively out to the sky. So this is what you want to see, right? You want to see a massive benefit in terms of how much heat you're delivering. What you don't really want to see is electrical performance penalties. Remember before I told you that we want to play this game where you're sacrificing one output for the benefit of the other. And so what we've been doing is kind of taking a slightly different direction. We've been saying, well, okay, is there a sort of a spectral splitting sort of design that we can think about? And we've been, by we, I mean here there's a spin-out company from that was formed a few years back to commercialize this kind of technology that came out of the project. And what you want to show is side-by-side systems like these where there's some kind of spectral splitting collector. Here we have a preferential absorption system where we try to absorb some of the part of the light and not send it to the cells. So side-by-side tested with the PV panel, right? But what you want to see is no reduction in the electrical performance from the PV, just pure thermal benefit relative to the PV, right? So I'm not sacrificing electricity to gain heat. And these are panels that we have. This is the roof of the Department of Chemical Engineering. We've done some tests. We have here some results which show and prove, right, that you can achieve exactly what I said. So you can have, this is a standalone PV panel, outdoor testing, around about 15% electrical conversion, right? So it's not the 20% that the manufacturer says, of course, because the manufacturer says 20% electrical efficiency. So it's not 20% because, of course, that's at 25 degrees, right? Once you take a PV panel, you put it on your roof and the temperature goes up, it's not going to be 20% anymore. It'll be something less than that. In our case, about 15%. And what you see here is, okay, it's the side-by-side, the spectral splitting collector here, giving you as much electricity as you would have from a pure PV panel plus whatever heat you can get, okay? So this is an example of us testing a real spectral splitting collector in outdoor conditions. I'll go quickly through a few other things. You can have PV windows. Here, the idea is, can you suppress or cut down the amount of infrared light going into a room at the same time while generating electricity and heat? And yes, there are ways to do this. I don't have time, unfortunately, to go into the details of these types of systems, but here we're sort of not just playing with electricity and heat, but we're performing an additional function, which is we're suppressing the infrared part of light from going into a building. Why would you want to do that? Well, because if your building is being heated up and you're switching on the air conditioning, for example, then suppressing infrared light that goes into a building basically just cuts down your cooling load, in addition to you delivering hot water and electricity and so on. And we've done some tests that I don't have time to go into that prove the same thing that we were saying before, that you can do all of this and get a pure benefit while not sacrificing electricity generated from these types of spectral splitting solar windows. We've spoken a lot about non-concentrating design. So you see these sort of flat panels. And of course, I said at the beginning that we're looking at distributed applications, right? But there are concentrating designs as well. And we've looked at that as well. Of course, the benefit of concentrating designs is that you can go to higher temperatures and then you can start decarbonizing industrial applications, all sorts of other applications where high temperature is needed. And here's one example project that we have in a, one way to concentrate light is with the parabolic trough. And we've got a project in collaboration with the Tecnológico de Monterrey in Mexico ongoing at the moment, where we're trying to, let's say, apply some of these design methodologies, spectral splitting, heat loss suppression, to this kind of parabolic trough type PVT system to see what benefits we can have. And there are real tests taking place in outdoors conditions in a facility down there in Mexico. Okay, so let me get to this hybrid PVX. I think this is really the last part before we can start wrapping up. So PVX is this idea that it might not be thermal energy that is useful to your end user. It might be that your end user needs clean water or cooling or fuel or something else. So PVT collectors are designed to generate, as the name says, electricity and heat. But maybe your end user doesn't need the heat, right? So PVX basically is a concept, quite a generic concept, where there's some kind of converter where the thermal energy gets converted to whatever else you want it to be, but this process happens inside the collector itself. So this is basically fundamentally different from us taking a PVT collector, taking the heat, and let's say giving that heat to some kind of desalination system that then delivers clean water, right? Here we're saying, can that process of desalination, for example, take place inside the collector itself in a synergistic way? In other words, that process requires a heat input to occur. That heat is coming from the cells, so you're getting the benefit of temperature reduction on the cell side, plus whatever else it is that you need. And that thing that you need is no longer heat, it's something else, right? So this is us looking at something called PVD, where we're performing desalination inside something we call a PV leaf. And here we have a passive system where we're pumping water through this type of system. We're evaporating at reasonably low temperatures and then recondensing the water and delivering it to an end user. I want to skip here. Yeah, and show you here some results where we can show that because of this process of evaporation of water, which is taking place internal to this PV leaf, you have a temperature reduction. So these lines out here are just conventional PV, and this is what would happen in the PVD system. So you have a temperature reduction, plus of course you have a water production rate, and we've achieved something like 1 liter per hour per square meter of cell or collector, if you like, in this type of system, proven experimentally. You can see here on the left-hand side this kind of PVD with some drops coming at the bottom being collected. So we basically just use a weighing scale to tell us how much we're generating. And here you can see relative to PV that we're not touching the electrical efficiency, right? So we're generating as much or more electricity than we're generating before. Plus we can get the water, plus we can get some heat because the water is hot and you can recover some heat from it. So this is the kind of thing that we're looking at the moment. You can also generate fuels. There's a paper that we submitted recently. I can't give you a reference because it's still under review, but there are ways, if you can think about, integrating some process, let's say in this case for generating hydrogen directly into the collector. There's some work that we're doing with the University of New South Wales again. So I'm going to go to the system level. It's quite quick. How are these systems actually used? Let's say you have your nice collector. It does wonderful, interesting things. There are lots of things that could be happening around it. Yes. So, okay, you have the sun coming in and then you have these electrical and thermal outputs. You can store those. You can convert them to cooling. You can store the cooling. You can use it at other times. You can have prices of electricity and gas and other energy vectors which vary with time. How do you control this? How does it operate? What is its economic and environmental potential in different sort of cases? And I'll just show you three very quick examples, one of which here is basically a PV hot water system, which this is a study we did in the UK where we were trying to answer the question, okay, for a given home with a given available roof space, there's only so much area you have available to install these types of systems. What is, right, the fraction of that home's electricity and hot water demand that you can displace, right, with these types of systems? There are different types of design variations you can have and operational variations you can have to the system, always asking the question, okay, how much of the home demand for electricity and hot water can you cover? And of course, what are the economics, right? So what is the payback period of this type of system or any other type of economic indicator you want to pick? You can go from electricity plus hot water to electricity plus cooling, right? So this is a PV cooling system and it's a very different application. This is a bigger system. This is some work we did in collaboration with some people in Italy for, you can see that the names at the bottom right-hand side, for dairy farms. So they have a cooling requirement. Again, the questions are the same. How to size the system, what type of environmental benefits do you have, what are the economics, how quickly the system pay back, and of course, how does it compete with alternative solutions, right? So how would it compete with just a PV solution, right, where you just use the electricity to drive some air conditioning or chillers to perform the same cooling that you'd have. And the final one that I have is, what if you have a need for all of these things? So you need heating, cooling, power at the same time. And yeah, there are integrated systems that can basically deliver multiple energy vectors, these so-called multi-generation systems. And the questions are the same as before, right? So you have these studies that tell us, how do you size the system, optimize its operation? What would be the economics? How quickly does it pay back? What fraction of the demands for heating, cooling, and electricity can you cover? And there's a picture that emerges, which is that these systems are very promising in terms of the environmental benefits. So you can always deliver more useful heat and total energy to an end user, but they're relatively expensive, relative to, let's say, just a PV system. And so we have to ask ourselves, okay, how deep do we want to go into deep decarbonization, right? If you want to, make further progress than just installing PV on your roof, of course, it's going to cost you something extra. You can imagine the complexity of these systems is greater than just PV. And that's it from me. I hope, just in summary, I've given you sort of a feeling for some challenges and solutions and design methodologies and approaches, and shown you, okay, what are we trying to do on a technology side, at the materials level, and also at the system level, trying to understand what are the economics and what's the benefit of different types of solutions and how do they compare with other alternatives out there. And I think with that, thank you for your attention, and I'll pass it back to whoever is moderating this for the questions. Thank you again for your attention.
Okay, thank you, Professor Pistos. Such a nice presentation. Now I would like to ask participants to ask question. If anyone have question, please type it in question and answer section. Okay, we don't have any question from participants.
I have 4 written here on the chat box.
Actually, that one is only for asking for sharing the presentation.
Okay.
I answered that.
I had a question actually, Christos. So I was just wondering, you were talking about the electrical performance and penalties, and I wondered if there's a lot of research happening in that area, or is that kind of?
Oh yes, I mean this, so the electrical performance, so we're going more toward photovoltaic technologies. Massive market, massive interest, lots of research, very, very big area. How do you, passively reject heat from conventional? So forgetting about PVT, right? Just thinking about photovoltaic solar panels, sorry. This kind of, how would you make minor changes to just conventional panels to cool them down? There are passive ways to do it, active ways to do it, so you could have things like fans blowing, you could have, there are very diverse types of approaches of how you can remove heat from PV panels. My personal feeling is that it's actually, of course, you pay a penalty, right? Because you have to incur the cost of installing whatever cooling system. And so the benefit that you have from this cooling has to outweigh the investment cost that you have for installing your cooling technology in the first place. And my personal feeling is that it's very, very difficult to come up with a pure PV cooling technology which is economically viable, right? In the sense that you will get an electricity benefit, but it's very difficult for that benefit to outweigh the cost that you have to install it. So my feeling is if you recover that heat, and that if that heat is either itself or through conversion to something else useful, and you can sell that in inverted commas, provide it to someone that has a need for it, that economic case is always easier than just rejecting it. So incurring the cost of the cooling system and then just rejecting it. At least if you recover it and deliver it, you have an additional revenue stream. So that's my feeling about that. It's a good question.
Thank you. Thank you.
So Kishore, we have one question. What are financial difference between the old methodology and PVX?
Yeah, it's a good question. Unfortunately, it doesn't have a simple answer because why? Because it's very, very case by case. So I would say the following: the benefits that your economic benefits are a function of the cost of implementing some solution and how much extra electricity and heat you might get relative to something else. And unfortunately, it's not possible to answer this question without saying, okay, where are you? What is the local climate? What is the ambient temperature? What's the irradiance level? And even more importantly, once you get into economics, what is the electricity price? What is the gas price? And so it kind of varies. There's a huge variability. Even if we take Europe, right, as a case study, and I'm sorry, I don't have slides to show you here, and we've done a little bit of this work, of course, but the ratio of electricity and heat, cost of gas to electricity, is just, such a scatter plot if you look at it in terms of, different countries incentivizing or disincentivizing different, one of these two, that it's very difficult to draw like a single conclusion. I think the answer to this is, it can be answered. It's just that it's very case by case. And if you want to look at some specific case study of interest to you, yeah, then it's possible to start looking into it. And it's reasonably straightforward, to have an estimate, but at least you need to, let's say, define the problem a little bit better.
Okay, thank you, Professor. The next question is, will these systems benefit with incident angle studies and by making modules that align the rays normally?
Yes, I mean, so this is like any solar technologies, right? The angle at which you if I understood the question correctly, the angle at which you install your panel is extremely important, and it depends also on the geography, right? So there'll be an optimum angle, in London, which is not the same as the optimal angle in Paris or Rome or wherever else in the world you are. So yes, the answer is they're sensitive. The output of these systems is sensitive to the installation characteristics, primarily the angle. And also due to that, you can start thinking about tracking, so you can think about 1-axis tracking, 2-axis tracking to kind of improve the performance. In everything that I've shown today, we're not investigating systems where, the panel's angle is changing during the day or during the season or during, to kind of optimize performance. These are just fixed panels, flat panels sitting on your roof. Again, the rationale being, it's easier to think of that as just being a product that people will install on their roof. So think about PV, right? You install the panel, you put it on your roof. You don't really need to think about, is there some kind of mechanism optimizing the angle at which the panel is? So it will play a role, but we're just setting it at some optimal angle, which depends on the geographical location that you're in.
Thank you, Professor. The further question is, does ray inclination prove to be a major factor?
So could you repeat that? Is the inclination angle?
Does ray inclination prove to be a major factor?
Yes, of course. Yes, very, very critical parameter.
Okay, thank you. So Caroline, please go ahead.
Thank you. I think that's all the questions. Thank you so much for your presentation today. It's really interesting to learn all about it. And thanks everyone for joining. And yeah, we look forward to receiving your submissions to ePrime, maybe even around this subject. So thanks again everyone for joining. We look forward to seeing you at the next webinar. Thanks. Bye.
Thank you very much. Bye-bye.
Thanks, Chris.
Thank you. Bye.